Assalamu alaikum everyone. This is Mati from Faculty of Engineering Sciences, and you're welcome in this online tutorial video. So in this tutorial video, we are going to discuss some problems from chapter 3 of Thomas calculus. So in chapter 3, we have learned some basic definitions and techniques to differentiate functions. So I will pick some random problems from the exercises and try to solve them. So here I have picked some questions from the random from the exercise, and the question is the check the differentiability or discuss the differentiability of this function at x is equal to 1. So basically this is from the section 3.1, and we have studied in 3.1 that how to calculate the derivative of functions at a point. So let's recall what was the definition of the function's derivative at a point. Like if we want to check the derivative at x naught, it will be calculated by using this definition, which is h approaches to 0, f of x naught plus h minus f of x naught by h. So we'll use this definition and try to solve this problem. So let's start the solution, and when we calculate f dash of want to calculate f dash of 1, it will be something like limit h approaches to 0, and now we'll replace x naught with 1, and it will be like x1 minus 1, and this plus h mod minus x naught is 1 minus 1 divided by h. And now we will solve this and compute if h, the limit of h exists at 0, then our function is differentiable at 1. If it fails to exist, then we can say that the derivative of this function is not exist at x is equal to 1. So when we further solve it, it will look like this is becomes 0, this is becomes 0, and we left with h mod by h, which is look like a absolute value function again, and we can now have to check the limit of this function. So when we split into piecewise functions and when we rewrite this function, let's say this is function of h, and we can rewrite it like this: minus h by h if x is less than, sorry, now we are discussing the function is in the form of h, so it will be h is less than 0, and h by h if h is greater than 0 or equal to 0. So now this is the function, and we need to calculate the limits, and we know how to calculate the limits for piecewise function. We have to find the left hand limit and the right hand limit, which we can calculate h approaches to 0 f of h, and this is the left hand limit, so we'll put minus over here to represent the left hand limit. And this is, from here we can see that the left hand side of h at 0 is this one, and we will use this function over here, and this will give us limit h approaches to 0 negative, and what we have here is 1 minus 1, so this is a constant number, so our answer will be minus 1. And similarly we can calculate the right hand limit of this function f of h, and this will be 1 and 1, so we can see that our left hand limit is not equal to right hand limit. So when we see situation like this, we can say that the limit h approaches to 0 f of h does not exist. So in this definition we have, you know, said that if our limit h approaches to 0 exists, then we can say that the derivative of the function at x naught exists, and we can see that our limit h approaches to 0, f of h does not exist. So we can say that this we cannot compute. We have not left with some constant values of some the function of x. So we can say by doing all this procedure that f dash of 1 does not exist. Question 2 is from section 3.6, and we are given three functions y, u, and w. Y is a function of u is a function of w, and w is a function of x. And we need to calculate dy by dx. And if we recall, in section 3.6, we have learned the chain rule. So we will calculate dy by dx by using chain rule. Let's write it down. What was the chain rule? It was dy by dx equal to dy by d, because y is a function of u, so we will differentiate this y with respect to u, and then du by dw, because u is a function of w, and then dw by dx. Okay, so let's start. First we will compute dy by du. It will give us dy by du. From here we can see that we have y is equal to square root of u, and this is a function of u, and we are calculating dy by du. So we're differentiating this with respect to u. So it will give us 1 by 2 square root of u, and after that we will compute du by dw, du by dw. And from here we can see that it will be, when we differentiate this u with respect to w, it will give us 2u plus e power u. And now we will compute dw by dx, and rw is secant x, and dy du by dx will be secant x into tan x. So now we need to put these values into our main formula, which was dy by dx, and let's make them the function of x. This is the function of u, and when we plug this u over here, it will give us 2 square root of w square plus e power u, w, and then w is a function of x, so we can compute 1 by 2. Now we will plug secant x here, secant square x plus e power secant x, and for this it will be 2 secant x plus e power secant x, and this is a function of x, so there's no need to change this one. And now we will substitute these three values here. It will be 1 by 2 square root of secant square x plus e power secant x, and 2 secant x plus e power secant x, and the third one is secant x into so tan x. So this is our final answer, dy by dx. So the next question is from section 3.7, and the question is find the normal to the curve that are parallel to the line this. So we need to calculate the equation for the normal line which is normal to this curve and which is parallel to this line. So the slope for the line and the slope for the normal will be same, because we know that if the lines are parallel, the slopes will be same. So we can compute uh, slope of normal line by this line. So convert this into mx, and from here we can see that our y is equal to minus 2x and our slope is minus 2. So now in next step we are going to find the tangent line by differentiating this curve, and after that, because the tangent line and the normal line are perpendicular to each other, and then we will use this slope, because by using the fact that if lines are perpendicular, m1 will be equal to minus 1 over m2 if m1 and m2 are slopes and lines are perpendicular, then the slope of each other will be found by using this relation. So let's differentiate this curve. This is an implicit equation, and we'll use implicit differentiation to compute dy by dx. So apply d by dx on xy plus d by dx on 2x minus d by dx on y, and the right hand side is 0, so d by dx of 0. From this we will apply product rule over here, because we have two functions x and y, and we will write x here and take derivative of y, which is dy by dx, plus now we will write y here and take the derivative of x, which will be d by dx of 1, plus now we will take the derivative of this term, and it will be using constant multiple rule. It will be 2 into 1, and here we have x minus this is dy by dx equal to 0. So from this we further solve it, x dy by dx plus this become 1, and this is y plus 2 minus dy by dx is equal to 0. And now we can see that we have two terms dy by dx, so we can rewrite it like this. So it will be dy by dx into x minus 1, and we can take these two terms on the right side and they will become minus y minus 2, and from here we can compute dy by dx by dividing this term on both sides. So this is dy by dx. If we can take minus as a common from these two terms, it will be we can rewrite it dy by dx is equal to y plus 2 1 minus x. So now this is the equation for the tangent to this curve, and as we know that the slope for tangent is minus 1 over the slope of the normal line, and the slope of normal line is m is equal to minus 2. So the slope for tangent line is -1 over m2, and it will be -1 over -2, it will be 1 over 2. So we can write it y plus 2 1 minus x is equal to, because this is the slope at xy point and we need to calculate those points, so it will be equal to 1 by 2. And by solving it further, we'll get y plus 2 is equal to 1 by 2 1 minus x, and 2y plus 4 is equal to 1 minus x. And if we eliminate, we make us x as a subject, so it will be x is equal to 1 minus 2y minus 4. Okay, so now this will become x is equal to minus 3 minus 2y. So now this is x, and to compute y, because these points are on the on this curve, so this x must satisfy when we substitute this x into the original curve equation. So it will be, let's plug this x into this curve. It will be minus 3 minus 2y into y plus 2 into minus 3 minus 2y minus y is equal to 0, and it is minus 3y minus 2y square minus 6 minus 4y minus y is equal to 0, and it will be 2y square. If we take minus common, it will be look like is 2y square, and then add them 3y 4y and y, this will become plus 8y minus, this become plus because we have take minus common from all terms. And now this is a quadratic equation and we need to calculate y's from here. So let's make the factorization. 2y square plus, it will be 2y square plus 2y plus 6y minus plus 6 is equal to 0, and 2y y plus 1 plus 6 into y plus 1 is equal to 0, and y plus 1 is equal to 0, and 2y plus 6 is equal to 0, and from here we get y is equal to minus 1 and y is equal to minus 3. Now plug these y's into x and we will get x is equal to, when we plug minus 1 here, it will give us minus 1, and when we plug this minus 3 here, we will get what it is, minus 6 plus 6 and minus 3 plus 3, so this is 3. So let's say that this is y1 and this is x1 and this is y2 and this is x2. Now we have points x1 y1, x2 y2, and we need to compute the equations for the normal, which has slope this minus 2, and by using equation line equation of a line which is y minus y1 is equal to m into x minus x1, and we have y1 here minus 1, so it will give us plus 1 and slope is minus 2, and x minus x1, this will be x plus 1. So now this is y is equal to minus 2x plus, this will be minus 2 and minus 3, minus 3. So this is our equation. This is our equation for the line 1, which is normal to this curve. And now to compute second equation, we will use same method. Y minus y2 is equal to m into x minus x2, and we have x1, x2 and y2, which is y minus, it will be plus 3, slope will be minus 2, x minus 3. Okay, so y is equal to minus 2x, and it is plus 6 and minus 3, and this equation is minus 2x plus 3. So here we have two lines. This is line 1, this is line 2, which are parallel to this curve, and this is the method to compute them.
This is question 4, and this is from section 3.8, and we need to compute dy by dx when we are given y is equal to natural log of some function. And we know how to compute. There are several ways. We can use either a chain rule on that function, or we can use outside inside function, which was outside inside rule was if we are given f of g of x functions in this form, so we will differentiate this function as f dash of g of x, and then we multiply with the derivative of the function of g of x. So we can use this one, but we can see that here is a natural log, and we also can use the properties of natural log, because if we don't use properties of natural log, it will be more complex. So let's start the solution. So the first property, I will write it. If we y is equal to, if we use natural logs property, here we have u by v form, and if natural log of a by b is given, we can write it natural log of a minus natural log of b, and this property holds for any logarithmic function. So we will write it natural log of square root sine x cos x minus natural log of 1 plus 2 natural log of x. So now we know another property, which is if we have natural log of a power something 2, like we can write it 2 natural log of a. So we will use that property also. Y is equal to, here we have power 1 over 2, so we can write it 1 by 2 natural log of sine x cos x and minus natural log of 1 plus 2 natural log of x. And the another property was a into b. If we are given this, we can write it natural log of a plus natural log of b. So we can apply that property also here. 1 by 2, and it will be natural log of sine x plus natural log of cos x and minus natural log of 1 plus 2 natural log of x. So these properties which we have used for the natural log make our function easier, and if you want to apply directly the derivative on this function, you also can do that, but maybe it is more difficult, become more difficult. So now we have y is equal to this function and which is equivalent to this function, and we now calculate the derivative and we apply the d by dx on both sides, and it will be dy by dx on this side, and when we apply 1 over 2 d by dx of natural log of sine x plus natural log of cos x minus d by dx of natural log of 1 plus 2 natural log of x. And now we will differentiate 1 by 2. The derivative of natural log of x is the derivative of natural log of x is equal to 1 by x. So we will write it 1 by sine x, and by outside inside rule we will differentiate sine x again and then multiply with this function, and it will be d by dx of sine x. Plus similarly we will write it 1 by cos x and then differentiate cos x. Okay, now for this side we will differentiate by outside inside rule. So first of all we will differentiate this natural log, which will give us 1 by 1 plus 2 natural log of x, and then we will differentiate d by dx of 1 plus 2 natural log of x. And in the next step it will be sine x. So derivative of sine x is cos x, so it will be cos x by sine x plus the derivative of cos x is minus sine x, so I will write it minus here instead of plus, so it will be sine x by cos x. And now for this part we have 1 plus 2 natural log of x, and the derivative of 1 is 0, and the derivative of 2 natural log of x is uh, 2, and the derivative of natural log of x is 1 by x, so it will be 2 by x. So this is it, we are done, but we are make it more simpler. 1 by 2, it will be cos by sine is, we know that the cot x, minus sine by cos is tan x, and minus it will be 2 by 1 plus 2 natural log of x, and this x we can write it here. Okay, so this is our dy by dx. Maybe if we use another method, maybe your answer is different, but the final thing is we have differentiate the function, and it is it.